My name is Michio Kaku, and today I want to invite you on a journey, one that begins not with catastrophe or cosmic drama, but with a quiet discovery that briefly placed our entire planetary defense system under a rare real-world test. In late December of 2024, as telescopes around the world scanned the night sky in their unending search for near-Earth objects, a small, seemingly ordinary asteroid entered our field of view. It was given a designation like so many others before it. 2024 YR4. Most asteroids we catalog slip quietly into the database, destined for a lifetime of harmless orbit predictions and occasional scientific curiosity. But this one behaved differently, and for a brief window of time, humanity collectively leaned a little closer to the cosmos. When the Atlas survey identified YR4 on December 27th, no alarms were raised. It was just one more faint dot drifting against the stars, its position measured, its motion plotted. The early data suggested nothing unusual. Astronomers are used to this rhythm: discover, measure, refine, and move on. Yet sometimes the cosmos reminds us that certainty is a privilege earned only through careful observation. And as more measurements of YR4 came in during the early weeks, something unexpected unfolded. Under normal circumstances, each additional observation tightens the predicted orbit of a newly discovered object. The cloud of uncertainty shrinks, the future path becomes clear, and if any initial risk existed, it usually fades into insignificance. But YR4 defied that familiar pattern. With each calculation, instead of narrowing, its orbital uncertainty widened in a peculiar direction, one that intersected with Earth's future position in the year 2032. It wasn't that the asteroid was on a collision course. Rather, the sparse early data simply allowed for a narrow set of trajectories that theoretically could lead to an Earth intersection. To the public, this may sound alarming, yet in science, uncertainty is not danger. It is merely the acknowledgement of what we still don't know. But when probabilities rise above certain thresholds, protocols are activated, not because the sky is falling, but because our system is designed to act with precision and caution. By late January, the estimated probability of impact climbed just above 3%. That number placed YR4 at level 3 on the Torino scale, the standardized measure we use to communicate impact risk. Most asteroids sit comfortably at level 0, posing no threat. Level 1 objects deserve routine monitoring. Level 2 indicates something slightly unusual, but level 3, this was new territory. No asteroid had ever occupied exactly that classification before. It did not mean danger was imminent. In fact, level 3 simply means pay attention, gather more data, proceed scientifically. But within the global planetary defense community, it was an unmistakable call to action. Almost immediately, the International Asteroid Warning Network issued a formal notice to observatories worldwide. Larger, more powerful telescopes, those capable of obtaining high-resolution measurements, were asked to contribute, and they responded. The Gran Telescopio Canarias, the Catalina Sky Survey, the Very Large Telescope, each institution allocated discretionary time to track this small but intriguing visitor. Watching this unfold, I felt a sense of admiration. The coordination was fast, disciplined, and rooted in scientific responsibility. There was no panic, only procedure. As observations intensified, humanity witnessed its planetary defense architecture moving in real time. We often think of cosmic threats as Hollywood-style emergencies, but in reality, the system is built on calm, methodical refinement. And indeed, once the new measurements were analyzed, the picture quickly clarified. The cloud of uncertainty shrank dramatically. The possible Earth-intersecting path evaporated. YR4 was not coming for us, not in 2032, not at any predicted time. The asteroid's rating dropped back to 0, returning it to the familiar category shared by countless harmless neighbors drifting through our cosmic backyard. But the universe always finds a way to make things interesting. As YR4's orbit became more precise, another possibility emerged. Not an Earth impact, but a small chance of striking the moon. Now let me be clear. Such an event would pose no danger to Earth. The Moon has no atmosphere to cushion impacts, and it has endured billions of years of cosmic bombardment. But for scientists, such a scenario holds extraordinary value. A fresh lunar crater created by a well-tracked asteroid would offer a scientific opportunity we rarely get, a natural experiment in crater formation, ejecta behavior, and near-lunar space dynamics. Lunar orbiters could observe the event with unparalleled precision. Still, it wasn't the potential moon impact that made YR4 scientifically important. It was the way this asteroid allowed us to test the global response system itself. For decades, planetary defense agencies have run simulations, drills, and hypothetical scenarios, but nothing compares to a real object with real uncertainty. In those early weeks, as observatories coordinated, communications flowed, and decision-making aligned seamlessly, we saw firsthand how the system performs under pressure, and that performance was impressive. But let us step back for a moment, because scientific curiosity naturally turns from external risk to internal nature. What kind of asteroid was YR4? What secrets lay beneath its rocky surface? Fortunately, the intense observation campaign generated a wealth of data, not just about its trajectory, but about its physical identity. One of the most remarkable discoveries was its rotation period. YR4 spins once every 19.5 minutes. That is incredibly fast for an object of its size. Many small asteroids are rubble piles, loose collections of rocks held together by gravity alone. Such bodies cannot spin rapidly without tearing themselves apart. Year 4, however, endures. This tells us something profound. It is likely monolithic, or at least far more cohesive than typical rubble pile asteroids. Its strong internal structure represents a window into the history of asteroid formation, perhaps a fragment of a larger parent body shattered long ago. Spectral analysis revealed even more. Different telescopes produced slightly different readings, sparking debate among researchers. But the general consensus points toward an S-type or K-type classification, rocky asteroids rich in silicates with moderate reflectivity. These characteristics matter. The composition affects how sunlight nudges the asteroid over long periods through the Yarkovsky effect, influencing its orbit over decades and centuries. Understanding this helps refine long-term predictions, not just for YR4, but for other similar objects yet to be discovered. As for its size, estimates place it between 40 and 70 meters in diameter. This size range is scientifically crucial, smaller than the dinosaur-killing asteroid, yet large enough to release significant energy if entering an atmosphere. An object like YR4, were it to hit Earth, could produce an airburst comparable to the 1908 Tunguska event, an explosion powerful enough to flatten forests over thousands of square kilometers. Thankfully, this asteroid poses no such risk, but studying it helps improve our models for others that might someday warrant closer attention. Year 4 offered something exceedingly rare, real-time insight into the behavior of the planetary defense system. It wasn't dramatic, it wasn't catastrophic, but it was meaningful, because sometimes the most valuable lessons come not from the spectacular, but from the subtle. As the days passed and the immediate concern faded, our attention shifted to what I believe is the heart of planetary science, understanding the deeper nature of an object that has just tested our defenses. When we realized that Earth was safe from any possible collision with 2024 YR4, the question naturally evolved from will it hit us to what exactly is it? Every asteroid tells a story about the early solar system, about the forces that shaped its existence, about the delicate balance of physics that governs every orbit and every rotation. The data gathered during the rapid observation campaign turned out to be a scientific treasure. Normally, small objects like YR4 do not receive this level of attention. Our telescopes are often busy, and planetary defense priority targets shift quickly. But this asteroid, due to that brief moment of uncertainty, became the focus of several world-class observatories. As a result, we gained insights far more detailed than what we typically obtain from objects in the 40 to 70 meter range. The first thing that stood out was the asteroid's astonishing rotation rate, just under 20 minutes per full rotation. For comparison, imagine a rock the size of a building spinning so quickly that its surface points escape the horizon in moments. Most asteroids of this size cannot maintain such speed without disintegrating. They are loose aggregations of dust and rock assembled through billions of years of gentle collisions. Their cohesion is weak, and rapid rotation would tear them apart. But YR4 holds together. Its fast spin is a silent announcement that it possesses strength, structure, and internal unity. This suggests that the asteroid is likely a monolithic fragment, a single coherent body rather than a loose rubble pile. This detail matters greatly to scientists. It tells us something about its origin, perhaps hinting that it was once part of a larger asteroid shattered by ancient impacts. When we look at objects like this, we essentially glimpse fossils from the dawn of the solar system, pieces that have survived 4.5 billion years of gravitational ballet, collisions, and solar winds. The next major clue came from its spectral fingerprint. When sunlight reflects off an asteroid, the wavelengths of that light carry information about the minerals on its surface. Different telescopes recorded slightly different brightness curves, and for a moment there was healthy scientific debate. But ultimately, the data converged toward a classification. YR4 appears to be either an S-type or a K-type asteroid. Both are rocky categories dominated by silicate materials. Such asteroids are common in the inner solar system. Their surfaces can be relatively reflective, their histories shaped by heat and ancient collisions. This aligns with its strong internal structure. Rocky bodies are generally more resistant to rapid spin than icy or loosely bound varieties. Composition influences more than appearance, it influences motion. Radiation from the sun imparts tiny pushes on small objects. Over years, these pushes accumulate in a phenomenon known as the Yarkovsky effect. Understanding how YR4 absorbs and re-emits heat helps refine long-term orbital predictions, not just for this asteroid, but for many others. The better we understand the physics of objects in this size class, the more accurate our planetary defense models become. Size estimates reinforce the importance of the asteroid. At 40 to 70 meters across, it occupies a crucial boundary in impact modeling. Objects smaller than this typically burn up or explode in the upper atmosphere. Larger ones can penetrate deeper and strike the surface. YR4 sits right at the cusp, a body capable of creating an airburst with energy comparable to the Tunguska event of 1908. That explosion flattened thousands of square kilometers of forest in Siberia. Thankfully, no populated areas were nearby. But it remains a stark reminder that even modestly sized asteroids cannot be ignored. Yet what intrigued the scientific community, perhaps even more than the object itself, was the possibility, however small, that YR4 could collide with the Moon in 2032. This potential impact does not threaten Earth, but from a scientific perspective, it presents a rare opportunity. Unlike Earth, the Moon has no atmosphere to cushion impacts. When an asteroid hits the lunar surface, the event is raw, unfiltered, pristine. A new crater is created instantly, ejecting material into space in a plume that orbiting spacecraft could observe with unrivaled clarity. Imagine being able to witness, with scientific precision, the formation of a fresh crater, its shape, its ejecta fields, its thermal signature. Lunar missions could capture high-resolution images of the event moments after impact. Observing such a crater would give us a clearer understanding of impact dynamics, subsurface material composition, and the distribution of debris in cislunar space. These insights would benefit not only lunar science, but also space exploration, especially as more satellites, stations, and possible lunar bases become active in the next decades. But the significance of YR4 did not stop at physical analysis. It extended into something equally valuable, the testing of our planetary defense mechanisms under real pressure. For decades, Scientists like myself have participated in drills, simulations, and tabletop exercises where hypothetical asteroids threaten Earth. These simulations train agencies to coordinate communication, sharpen analysis, and practice response strategies. But there is always a difference between simulation and reality. A real object, one with a non-zero impact probability, creates an entirely different environment of urgency and cooperation. With 4 dinars, humanity received a rare gift, a controlled stress test, not a crisis, not a threat, but a moment where the system was activated for a real object, allowing scientists and agencies to see exactly how global coordination performs when it truly matters. The precision of communication, the speed of observation requests, the sharing of data across continents, all of it unfolded smoothly. The system worked. And for the first time, the Torino scale classification of level 3 was not theoretical. It was applied in practice, guiding decisions and resource allocation without triggering unnecessary alarm. This real-world rehearsal exposed strengths, rapid mobilization, clear communication channels, accurate modeling, and also small gaps, technical bottlenecks, limits on observation time, the need for better access to data for smaller observatories. All of these insights will strengthen the network for the next real test. And unlike drills, which end once the scenario concludes, the lessons from YR4 are now etched into the collective memory of the planetary defense community. That is why this asteroid matters, not because it threatened Earth, not because it will reshape the Moon, but because it revealed how the machinery of science, observation, and global cooperation functions under genuine uncertainty. In this way, YR4 became a scientific mirror, reflecting both our preparedness and our areas for improvement. It reminded us that planetary defense is not merely about predicting the next impact. It is about building a resilient, collaborative, and scientifically grounded response system, one capable of acting calmly and decisively when the next unusual object appears on our screens. If there is one lesson to take from YR4, it is this: meaningful progress in protecting our planet does not always arrive wrapped in catastrophe. Sometimes it emerges quietly from a small asteroid spinning through the darkness, challenging us to measure, analyze, and act with precision. As the data settled and the orbit of 2024 YR4 reached clarity, the event transitioned from an active investigation into a reflective moment for the scientific community. We now understood that the asteroid posed no threat to Earth, that its brief lunar impact possibility was scientifically intriguing but not alarming, and that its physical characteristics offered a new thread in the story of our solar system's evolution. But perhaps the deepest value of this event lies not in the asteroid itself, but in what it revealed about the future of planetary defense, our readiness, our vulnerabilities, and our responsibilities as a species living in a cosmic shooting gallery. Year 4 reminded us of a simple truth: early uncertainty is inevitable. Even in an age of powerful telescopes and automated sky surveys, a newly discovered object can still arrive with limited data, ambiguous motion, and predictions that shift as days pass. In the case of YR4, the initial widening of its uncertainty window was not a warning of doom, but a demonstration of how sensitive orbital projections are to small gaps in early observations. The only antidote is rapid global cooperation, precisely what unfolded. But as impressive as the response was, the incident also underscored why the future of planetary defense depends on enhanced early detection systems. Projects like NASA's NEO Surveyor and the European Space Agency's NEOMIR mission are designed exactly for this purpose: to find smaller, harder to detect asteroids long before they drift into periods of uncertainty. Unlike ground-based telescopes, which struggle to spot objects approaching from the direction of the Sun, these missions will operate from space, scanning infrared wavelengths that reveal dark, warm, and faint asteroids we currently miss. Year 4 ultimately proved harmless, but it provided a clear demonstration of how critical early detection is. With more data earlier, its risk window would have closed sooner. The incident also broadened our perspective on what planetary defense truly encompasses. We often think of it as Earth defense, protecting our planet from hazardous impacts. But YR4's small chance of striking the moon reminded us that the celestial neighborhood is interconnected. An impact on the lunar surface would not threaten life on Earth, but it could generate debris trajectories that move unpredictably through cislunar space. As humanity expands its presence beyond Earth, with more satellites, lunar missions, communication relays, and eventual habitats, the space between Earth and the Moon becomes an area of growing strategic and scientific importance. Understanding how impacts behave in this region matters more with each passing year. What I found particularly encouraging was how the international cooperation mechanisms responded. The International Asteroid Warning Network functioned as intended, communicating findings, coordinating observations, issuing calls for data, and ensuring that even nations with smaller observatories had access to critical information. Planetary defense is not a national effort, it is a global one. Asteroids do not recognize borders. They do not care about politics. They move according to the laws of physics, not geopolitics. And if one ever threatens Earth, we will only succeed by standing together as a scientific civilization. The smooth response to YR4 reaffirmed that we are capable of that unity. Yet the event also served as a quiet reminder that our system can still improve. Access to real-time data remains uneven across scientific institutions. Observation time is limited, and smaller programs often struggle to contribute because of resource constraints. If YR4 had continued to display ambiguous behavior for longer, competition for larger telescope time would have intensified. But rather than interpreting these as shortcomings, we should view them as blueprints for progress. Every unexpected asteroid teaches us where to strengthen the system. Now, as scientists refine YR4's orbit over the next decade, each new observational window will further reduce its lunar impact uncertainty. Perhaps the asteroid will miss entirely. Perhaps it will meet the moon and create a fresh crater. Either outcome is scientifically meaningful. Even if it remains just another member of the near-Earth object population, the data gathered from this brief episode will remain invaluable, informing future models, calibrating simulations, and improving our strategies for the next object that behaves unpredictably. And make no mistake, there will be a next object. Somewhere in the darkness of space, another small asteroid is already on its path toward discovery, perhaps with an orbit full of ambiguity, perhaps with a trajectory that requires our attention. But thanks to events like YR4, we are increasingly prepared. We have systems that mobilize globally, scientists who collaborate across continents, telescopes that can be rapidly tasked, and a public that is increasingly informed about the realities of near-Earth objects. In the end, 2024 YR4 did not bring fear. It brought clarity. It reminded us that planetary defense is not defined solely by dramatic threats, but by the quiet, everyday work of surveying the sky, analyzing trajectories, and preparing for possibilities. Progress often appears in subtle forms, in algorithms refined, in communication tested, in orbit predictions sharpened. Year 4 offered all of these without escalating into a crisis. As we continue to explore the cosmos, we must remember that our story is intertwined with the story of every rock, every comet, every fragment drifting through our solar system. These objects are remnants of creation, messengers from the past, and occasionally teachers that reveal how well we safeguard our future. The asteroid 2024 YR4 may fade from headlines and databases, but the lessons it provided will resonate throughout the planetary defense community for years to come. In science, significance is not measured solely by danger, but by insight. And in that sense, YR4 was a gift, a reminder that knowledge, preparation, and global cooperation are our greatest shields against the unknown. As we look forward to future discoveries, we do so with greater confidence, knowing that each unusual object brings us closer to understanding not only the cosmos, but our place within it.